In this video, I want to take a look at the Laplace transform of a derivative of a function and the Laplace transform of the second derivative and third derivative and so on. We will be using Laplace transforms to help us solve differential equations that have higher and higher order derivatives of the function that we're trying to solve for. So we're going to need to know what is the Laplace transform of those higher derivatives. So here's the basic theorem. If f is a continuous function, and the derivative is a piecewise continuous function on any interval from 0 to a. We should point out that I don't know that I haven't used the word piecewise continuous yet, but essentially take the interval from 0 to a, cut it up into finitely many pieces. If on each piece the function is continuous, then we call it a piecewise continuous function. Now, the function itself may not be continuous because there's breaks, but if there's only finitely many breaks, then we would call it piecewise continuous. And I need there to be three numbers, k, a, and m, such that the absolute value of f is less than or equal to k times e to the a t for all t bigger than m. So this is like what I said in one of the videos for section 6.1, right? That the functions that we're dealing with here and going to be taking Laplace transforms of are ones where they have to be growing less fast than an exponential, right? So this is the exponential e to the at, k is just some scalar of that. And so we're saying that the absolute value of f has got to be smaller than this exponential function for all t bigger than some starting point. Okay, so yeah, we got a function. It can be growing. This could be a positive e to the at, but as long as the a could be positive there, but as long as f is growing more slowly than that, then we're fine. So the conclusion is, if you've got all that, then the Laplace transform of the derivative of f is s times the Laplace transform of f minus f0. F at 0, right? Plug 0 in, see what the function is. Here's the proof. It's pretty straightforward. The Laplace transform of f prime of t is, by definition, the integral from 0 to infinity of e to the minus st times f prime of t dt, right? That's the way you take Laplace transform of any function. You just multiply it by that exponential and then integrate from 0 to infinity. Now this, it turns out, happens to be very easily done by parts. So I'm going to let the exponential be the u and the f prime of t dt be the dv. This is a really nice thing to make dv because what is the antiderivative of the derivative of f? Well, it's f, so that's the v, and then the exponential is easy enough to take the derivative. You get that exponential back times the derivative of the exponent, that's the chain rule, so I got a minus s that pops out in front here. So the integral of u dv is u times v minus the integral of v du. So here's the u times v. It's going to be evaluated between 0 and infinity, and then I'm going to subtract the integral of v du. Now there's a couple of things going on here, going from here to the next line. One is the minus minus is going to become plus, and the s can be written out in front. So that's that right there. Now this stuff, I'm going to plug in the infinity and I'm going to plug in the 0. So there's the infinity plugged in, there's the 0 plugged in. Now what the heck does this mean? Remember, what we're doing is we're taking a limit of plugging a big number in and letting that big number go to infinity. Right? So this is big number, big number. And up above, we assumed that f was growing no faster than this exponential e to the at. So if s is made bigger than a, okay, then this would be a decreasing exponential. So this is headed towards 0. And this would be potentially an increasing exponential, but it's increasing no faster than e to the a. And this would be decreasing faster than e to the minus a. And the 0 would win, right? So as long as s is bigger than a, and this function is growing no faster than an exponential, then we can say that this is headed to 0. So there's a 0 out in front here, And then this thing just turns into an e to the 0, which is 1, so that's just f of 0. Literally the function evaluated with at 0 plugged in. And then this right here now, I claim, look at that, the integral of e to the minus s f e to the integral of minus st times f of t dt. This is the Laplace transform of f. So that's what I have right there, and there's an s out in front. And so that is what the theorem was we were trying to prove. Laplace transform of the derivative is s times the Laplace transform of the function minus the function evaluated at 0. Okay. Now, because I have that, I can do higher order derivatives too. So let's scroll up here and see some higher order derivatives. Second order. Well, the thing is, the second derivative is the first derivative of the first derivative. So we can just use that theorem above and say the Laplace transform of this function is s times the Laplace transform of the antiderivative, right, minus the antiderivative evaluated at 0. Now I'm saying an antiderivative. The theorem didn't say antiderivative. I'm using f prime and f, but if this was an f, then this would be the antiderivative here, right? So that's why I'm using that terminology right now. It just bumps up by one derivative, and then you've got that thing right there evaluated at 0. But now the Laplace transform of the derivative is this. We can just do it again because we got one more antiderivative we could do. Distributing the s through, I get that the Laplace transform of the second derivative is s squared times the Laplace transform of the function itself minus s times the function evaluated at 0 minus the derivative evaluated at 0. Now I could do the third derivative by saying, hey, the third derivative is the first derivative of the second derivative. So using the original rule that this would be s times the Laplace transform of the second derivative minus the second derivative evaluated at 0. But we just calculated that the Laplace transform of the second derivative is all this stuff. So I plug all that stuff in parentheses and distribute the s through and find that the Laplace transform of the third derivative is s cubed times the Laplace transform of the function minus s squared times the function evaluated at 0 minus s times the derivative evaluated at 0 minus this should say the second derivative evaluated at 0. And now it does. I just learned something about LMAP, that when I'm typing in a second derivative, well, the first derivative I just type f and a single quote. To do a second derivative, I have to do an f and two single quotes. Sometimes I just do a double quote, but a double quote doesn't get recognized as a derivative, and LMAP just ignores it. Anyway, that's why it didn't look like it had a second derivative there, but it is. And the general formula for the Laplace transform of the nth derivative is going to be s to the n times the Laplace transform of the function itself minus s to the n minus 1, f of 0 minus s to the n minus 2, f prime of 0, and so on. Just keep bumping the power of s down by 1 and increasing the derivatives evaluated at 0 until you get to the n minus first derivative evaluated at 0. Okay. Let's do one example of how this is going to help us solve differential equations, and then in future videos I'll do a bunch more examples. But just want to do one simple one to see what's happening here. So we're going to start with a differential equation. And I'm picking a really simple one that I think we can just do by inspection. Do you know any functions that when you take the derivative and add it to itself gives you 0? Well, that would be the same as saying y prime equals minus y. It's like, yeah, e to the minus x or e to the minus t. Well, what is our independent variable here? I think we're using t's. I'm also going to give an initial condition here with y of 0 equal to 7. Okay. So here's what I'm going to do. I'm going to take the Laplace transform on both sides. So Laplace transform on the left-hand side equals the Laplace transform on the right-hand side. Now notice, we proved in a previous video that the Laplace transform is a linear operator. And because of that, the Laplace transform of 0 has to be 0. Any linear transformation sends 0 to 0. So this is definitely a 0 on this side. We've also showed that the Laplace transform of a sum is the sum of, I mean, it's linear, so the Laplace transform of a sum is the sum of the Laplace transforms. And now the Laplace transform of y prime is s times Laplace transform of y minus y of 0. So I know what y of 0, that's my initial condition. Plug the 7 in there. And then do a little bit of algebra. Slide the 7 over, factor the L of y out, and solve for L of y. So what I've done to this point is I haven't solved the differential equation. I've solved for the Laplace transform of the solution to the differential equation. Right? Y is what I'm looking for. Y is the function that's going to satisfy this differential equation. And I have its Laplace transform. So what I need to do now is I need to do an inverse Laplace transform. I have to say, I know the Laplace transform. What function did it come from? Okay. There's methods that we'll talk about to some extent, but for now, I just want to say, in a previous video, notice that I showed that the Laplace transform of e to the at was 1 over s minus a. And so what I have here is, well, factor the 7 out, because if the Laplace transform is linear, then the inverse is also linear, so the 7 can just be factored out, and I've got the inverse Laplace transform. That y is 7 times the inverse Laplace transform of 1 over s plus 1. This looks a lot like that with a equal to negative 1. So the inverse Laplace transform of 1 over s plus 1 is e to the negative t, and the 7 comes along for the ride. And sure enough, the solution to the differential equation is some constant times e to the negative t, and that constant is just the right one, so that when you plug a 0 in, you get 7 as an output. This was a pretty simple first order equation, and we will be able to do this with much higher order equations, but at least you can see where this is headed. So what we need to do in the upcoming videos is we need to talk about how do you do inverse Laplace transforms and do a few examples of solving higher order differential equations. Stay tuned.